Thus far, you've mainly learned about the PV module and maximum power point tracking. Now it's time to look at other aspects of a PV system. These are the so-called balance of system items. Understanding how the PV module works is really important. As a PV system engineer, you need to know how all the other aspects of the PV system work as well. One item that you may not have realized is very important is the cables. So in this video, we are going to look at them in detail. Here, you will learn about the different categories of cables, color coding of cables, followed by power and voltage losses in a cable. Cables are used throughout the PV system. They have to be used to connect the PV modules to the power electronics. They are also used to connect the power electronics to the loads. As I said before, you can see from our overview of the PV system components that cables fall under the balance of systems. This encompasses components from the system aside from the PV modules and the loads. There are a few categories of cables you should be interested in. DC cables are the cables that go between the PV modules and the power electronics. If the PV system is an off-grid system, you'll also use DC cables between the battery bank and the power electronics as well. Sometimes DC cables are color-coded, and if they are, red cables are connected to the positive terminals on modules or batteries, and black cables are connected to the negative terminals of modules and batteries. However, some systems are completely wired with black cables. These cables are relatively thick compared to AC cables since they usually operate at lower voltages. Speaking of AC cables, they are also used in PV systems. Typically, these cables are a bit thinner than the ones used for DC connections. There are usually 3 cables used in single-phase AC power. These are the phase wire, the neutral wire, and the ground wire. The color code for these cables depends on the country you are in. For example, in the European Union, brown cables are used for the phase, blue cables are used for the neutral wire, and green-yellow cables are used for the ground connection. So far, I alluded to the fact that DC cables are generally thicker than AC cables. But what are those thicknesses that we use? Generally, for DC cables, connecting solar batteries and power electronics, thicknesses range from 4 to 16 square millimeters in cross-section. Cables interconnecting batteries are generally thicker as they need to be able to handle very high currents. These cables can range from 25 to 35 square millimeters. Finally, AC cables from the inverter to the loads can generally be in the range of 1.5 to 2.5 square millimeters. Why do we need to choose these thicknesses? Well, there are 2 main aspects to consider. The first is power loss. Though wires are great conductors of electricity, they still always dissipate some power when current flows through them. This power dissipation depends on the amount of current, the length of the cable, the thickness of the cable, and the material used to make the cable. More current and a longer cable and a thinner cable all result in greater power loss. So how can we calculate this? Well, the power dissipated is equal to the current squared times the resistance of the cable. Alternatively, we can use the voltage drop over the cable squared divided by the resistance of the cable. But how can we determine the resistance of the cable? Using the basic formula for resistance of any conductor, the resistance is equal to the resistivity, ρ, times the length of the cable divided by the cross-sectional area. Ρ can also be replaced by 1 over the conductivity, sigma. A higher conductivity means that the same amount of wire will have lower resistance. Here you can see some typical conductivity values for copper and aluminum. You can see that copper is almost twice as conductive as aluminum. Now, you can look at the dimensions of the cable. A longer cable means that the current has more material to flow through. This means a greater resistance. A smaller cross-sectional area means that there's a tighter path to flow through, so that also increases the resistance. So in general, using shorter and thicker cables reduce power loss. So why don't we always just use extremely thick cables? Well, the problem is material cost. Therefore, we always try to use as thin a cable as possible that still meets the power requirements of our system. So we have been discussing power losses. Of course, you can always look at this as an efficiency. Here, eta C refers to the efficiency of the cables. It is defined by the DC power generated by the PV modules, PDC, minus the sum of all the power losses of the cables divided by that DC power. So far we've discussed power loss in the cables, but that is not the only cost when using long cables. Voltage losses also need to be considered. Here we can simplify a PV module to a voltage source, and we can attach it to a load through two identical cables with a resistance of R_cable. Of course, there will be some current flowing through the cable. The voltage at the load will therefore be the PV voltage minus the voltage losses over the cables, which in this case is equal to 2 times IPV times the cable resistance. Now you understand some of the important considerations when it comes to cables. You learned about cable types in terms of DC and AC. You also learned about color coding of cables. Finally, you learned about power and voltage losses in our cables. You'll need to take these into account to properly model a complete PV system. Furthermore, as an engineer, you have to understand these losses in order to properly design any PV system.